going to get weird. It already has been. What is this stuff? What topic are we going into? Polar land. Locating things in space can be done many ways. Locating things in space can be done many ways. We like doing it this way. Certain horizontal position, certain vertical position. Another way to do that is to measure a point's distance from the origin and the degree measure that ray makes with the positive x-axis. With the positive x-axis. So you need to know a distance and you need to know a angle measure. Yay! So what's the, for Q here, what's the distance Q is from the origin? 5. What's the angle measure from the x-axis? So in this case, what's the Cartesian coordinate for this point? No, 5, 0 is the Cartesian coordinate, right? What's the polar coordinate? Yeah.
R is 5, the angle is 0.
Yeah, so 5, 0 actually again. So is it possible for them to be the same? Yes, it is. Okay. Is it going to change? Absolutely. So here, let's say this was 3 and 4. So let's say this coordinate in Cartesian land was 3, 4, right here. 3, 4. So what's the distance from the origin to you?
5.
It's 5. Right, exactly. So if we want to actually find the theta value, there's a few ways. But we now know that the distance from here to here, assuming that's the point 3, 4, that distance is 5. So r is 5. To get the second value, and that's 3, 4, not 3, 9, you need that theta value. Which trig function are we going to use?
Use a lot.
You can use a lot of them at this point.
Any of them.
Any of them. But if you have 3, 4, what could you use straight off? Tangent, right? So we know that tangent of what is theta?
3 over 4.
Tangent is,
4 over 3. No.
is it 3 over 4 or 4 over 3?
4 over 3. Yeah,
Hold on.
4 over 3.
Tangent, excuse me,
Theta.
tangent of theta is equal to what?
Theta is 4 over 3.
Is it 4 over 3 or 3 over 4? 4 over 3. Ah, okay. Got it. So if we want theta, we have arctan of 4 over 3 is equal to theta. Very nice. So if I gave you bunches of points, could you convert them from polar to Cartesian and back again? With some practice. With some practice. Here's the summary, though. The bottom here. I'll leave it right here. Generally speaking, if you have x and y, if you have the Cartesian coordinates, x is equal to r cosine theta, and y is equal to r sine theta. So if you know r and theta, you can find x and y. If you have x and y, you can get r. And if you have x and y, what did we just do? We found theta. Congratulations. We can convert. Very nice. Awesome. Exciting. So, a few questions here. A and B. It says, how do you find the r value? R is, look up there. What do you see for r? Plus y. Oh, and that's not a highlighter. This is a highlighter. There we go. So r is going to be the square root of 3 squared plus 4. So we already did this one, so we know r is 5. Nice. And we know that the theta value is going to be tan inverse of what? 4 over 3. Why do I keep it as tan inverse of 4 over 3? Because is that a very nice degree value? Or no, it's not very nice. So if we were going to write this as r theta, it would be 5 comma tan inverse of 4 over 3. Exciting. What about this one? Over 0, down 5. What's the distance away from the origin? 5. And if you've gone straight down 5, what's your degree measure? You're going counterclockwise from the positive x. It's going to be 3 pi over. Good. What helps when you're graphing things in polar land is paper that looks like this. Because what do you get? You have concentric circles making a bullseye, which measure the distance from the origin, right? And then you have maybe your trig, the basic trig. Well, there's not all of them there, but your basic trig values. So can you use this as, is this polar graph paper? Yeah, this is polar graph paper. You can graph things in polar land this way. You go out a certain distance, and then you rotate, you draw a point. Are polar functions going to look pretty?
Yes.
Say yes. They look really pretty. I know, you're like, it's subjective, but we kind of agree with Mr. Seamon. What shapes do you get to make that look really cool? You have to make pretty flowers. Limacons and all sorts of neat lima bean shaped things. It's very exciting.
What shape is a lima bean?
Exactly. It's a limacon. Very exciting. Okay. So this is the unit circle. So y equals 1. What is, we know what y equals 1 is. It's a, what is y equals 1? It's a line. What type of line? Can you be a little bit more? It's, yes, all lines are straight. Could draw with a ruler. It's a horizontal line. Yeah, horizontal line. So the point of looking at these though are certain functions that are complicated in one are much easier to write in the other form. For example, r equals 1. Does it get any simpler than that?
No.
No. We actually know what the unit circle is. What is the equation for the unit circle in Cartesian? X squared plus. And where does that come from? Well, we know r is equal to the square root of x squared plus y squared, as we stated, right? So what does r squared equal? X squared plus y squared. So if r is always 1, what do we have? Oh, there it is. Now here's where it gets even more fun. What about this? Write the equation for y equals 1 using polar coordinates. How do we do that? R sine theta. Oh, we know y equals 1, so we now know that r sine theta is equal to 1.
You could like divide.
You could divide. So it depends on do you want r in terms of theta or excess. So what is this? R is equal to 1 over sine theta. Oh, there it is. So sometimes it's not that bad to convert, but sometimes it's impossible or really annoying. So for example, imagine one of those pretty flowers that we're going to see. You've seen those flowers before where you have these like cool petals and sometimes there's a petal inside a petal, that kind of thing. Relatively simple to do in polar land. What happens if you try to take a flower and turn it into Cartesian?
You die.
First of all, it would have to be parametric.
It would have to be, A, it would help if it's a parametric, and B, are flowers generally functions in Cartesian land? No, they really don't pass the vertical line test, right? So you're gonna have to do like pieces of it, right? You're gonna be like, for this section it's this, for this is, and you've done that before maybe, where you can draw pretty pictures by doing lots of piecewise functions. But sometimes it's gonna be relatively straightforward to convert functions, and sometimes it's going to just not be possible at all. The challenge is that polar equations look pretty sexy, not just visually, but in written form. It's like r is equal to 3 sine theta plus 5, and you get this cool graph. It's not that hard to write down, but if I ask you to translate it into Cartesian, sometimes it's 2 steps, and sometimes it ain't happening at all. Just remember that. Please remember that. I can guarantee at some point in the next 2 days.
That, on the x-axis.
What's
On the right side.
what's 3 sine of 2 times 0? 0. So it starts at, what's that point called? Origin. And it actually graphed this. What the calculator does, it just plots points, right? Calculator ain't doing algebra. It's just going da, 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 right? Where does it go? Does it go up or down, left or right? What's it do? You might have seen it. What did it do? You can put your hands down. It goes like this, right?
Yeah.
It went like this?
Yeah.
What was the theta value when it got back to 0? So it gets back to 0 after a loop, right? It starts here and it goes, it comes back around. Pi over 4, pi over 2, what is it?
Pi over 2, right?
You need it to be 0, right? Look at the original equation. What's the original equation, everybody? 3 sine 2 theta, right?
Yeah.
So sine pi over 2, because pi over 2 times 2 is pi. Sine of pi is 0. So what does it do here? So this petal right here is 0 to what? Pi over 2. Where does it go next? Which petal does it do next? Bottom right, top left, bottom left. Which one?
Right.
Is it the third quadrant next?
No, it's the bottom right.
Bottom right?
Yeah, because it goes down.
Bottom right, so it's the fourth quadrant?
Yeah.
What do we think? It is bottom right? Okay. Okay. So we think it goes like this next? So what is that going to be? That's going to be pi over 2 to what? To pi. And then where does it go?
Then it goes bottom
What
left.
quadrant? Bottom left?
Yeah.
Goes to this one next?
Yeah.
Okay. So that's going to be pi to what? 3 pi over 2?
Yeah.
And then it goes up here, right?
And it goes, that's
3 pi over 2 to what? 2 pi. Very cool. What happens if, I have a question, if I change my window, everybody, if I change this to, let's say, I don't know, 100 pi, what would happen to the shape of my graph? Nothing. If I were to graph this, what's it actually doing? Oh, look, boom, 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 boom. What's it still doing? It doesn't actually show it, but what's it doing? It's drawing over itself. This is the biggest way you can mess up questions about polars. You will understand what they look like, you will set up the integral, and you will mess it up because you will set the limits of integration wrong. This is what I mean. Can you see that it's drawing over itself? No. You can easily choose the wrong starting and end points, or make it much harder than it needs to be. So for example, we're going to do the, like, what's the area of this thing? It's not that hard actually. We can do the area of this thing. We're going to set up an integral. we're going to start at 0, and we could go to 2 pi. We could. That would go. Hey, what do you notice about this? There's a lot of symmetry, right? How many petals do you see?
4.
Are they all the same?
Yes.
So you can take one of the petals and multiply it by 4. So you'll need to be very careful about what is one of the petals. From 0 to what? To pi over 2. You have to be super careful about it. You have to be super careful about it. So you could do 4 times the integral from 0 to pi over 2 of the formula that I'm going to give you. Biggest, easiest thing to do wrong is not take care of overlap. It's probably still from geometry land. What's the area of an entire circle, everybody? Pi r squared. Nice. What percentage of this whole circle is this? Meaning, how many degrees all the way around in radians? How many degrees in radians? 2 pi radians, right? So how much of the circle is this? Pi over 2. It's theta over 2 pi. This is how much of the circle this sector is, right? And what is this? The entire area. So if you wanted 50% of a tank of water, you multiply the volume of the tank of water times 50%. This is how much of the circle we have, and this is the area of the entire circle. When you multiply these together, what do you end up with? The pi's cancel. You end up with 1/2 r squared theta. 1/2 r squared theta is the area of one sector. When we were doing integrals in Cartesian land, we were adding up an infinite number of what? Rectangles. We had delta x and a height, right? You know, integral a to b of f of x dx was the height times an infinitesimally small width, and we did an infinite number of them. We used Riemann sums first. You got real frustrated, and then you could use the fundamental theory of calculus and use integrals. Yay! We're not adding up rectangles anymore. What are we adding up? Sectors. We're sweeping out sectors instead of scanning from left to right, or right to left and inverting, whatever. You're doing a spotlight. You're starting in the middle, and you're going to add up all of these sectors going all the way around. It's 1/2 r squared theta, and it's pretty freaking. I think, again, I don't like using the word easier or simple because those are evil words to use in math, but I like it because it comes down to this. What do you see? 1/2 r squared theta, where r is written in terms of theta. R is equal to f of theta. What do you see? 1/2 r squared d theta, an infinitesimally small slice. We're doing little tiny pizza slices. That's it. Little tiny pizza slices. And alpha to beta is the thing that gets messed up so many times. Alpha to beta is the starting theta value and the end theta value. And then it's just doing the integral. So for example, here's a shape. Oh, did we see that already? Yeah, absolutely. Can someone tell me what integral they would solve? Don't solve it, but what integral would the area of just that petal be? What would just that petal be? Yeah, go ahead.